Welcome to lecture 9 of the Language Models and Intelligent Agentic Systems course. Today's lecture is on reward hacking and goal misgeneralization. So let's dive straight in. What are we going to talk about today? Well, last time we introduced a framework of learned optimization. That was when we're using some base optimizer to train a measure optimizer. So this is like a process of training an agent that has goals that pursues an objective. What can go wrong? We'll first look at this at a high level, and then we'll isolate kind of two specific failure modes which are particularly interesting. The first is reward hacking, and the second is goal misgeneralization. So yeah, let's dive straight in. But I'm going to start with a story. So these behaviors I'm going to kind of try and explain and give you lots of examples throughout today. I think they're best understood with examples, and it's probably easiest to start with a human example. So I'm going to start by talking about a rat massacre. So imagine you are in Hanoi, Vietnam, 1902, and the city is plagued by rats. The French are in charge of Hanoi at that time, and they decide to take action. So they put a bounty on rats, but to make sure that people actually kill rats, to claim the bounty, you have to provide a rat tail as proof and hand it in to the authorities. So yeah, people start killing rats, hunting them down, cutting off the tails, handing it into the authorities. But the population of rats doesn't really seem to go down much. If anything, it's worse than ever. And then something slightly weird happens. People start noticing rats with no tails. What's gone on? Well, rat catchers would hunt rats and then release the rats back into the wild once they'd cut the tails off. Because it's much easier just to release a rat than to go through the worry of dealing with the body. And if you release it, then it's likely to create more rats and you've got more business as a rat catcher. Some people even started to breed rats and then cut the tails off in captivity before releasing them to the wild. So this this reward, this bounty that the authorities placed on rats was meant to encourage people to hunt the rats, but instead it led to a completely different outcome, which really wasn't desired and was much worse than the original situation. And it turns out this is not an isolated story. This is a pretty common phenomenon when dealing with systems of humans, and it's even got a name called Goodhart's law. And so this is succinctly described as the following. When a measure becomes a target, it ceases to be a good measure. And many of you will have heard this before. I'm just going to give a few more examples just to build loads of intuition here. So if you're a hospital, you might have a target of reducing the length of stay of patients. And this is meant to prove that you're making patients get better faster. But it's very gameable. It's very easy just to kick patients out earlier. And as the hospital manager, if you just kick patients out early, you really do reduce your length of stay, but this is very bad for patient outcomes. If you're a scientist, you might really publish a really high volume of works that make very incremental progress because that gets you the most citations but doesn't really progress the field. If you're a school, you might really push towards students getting very high grades in exams because that's all that parents can see. That's what the school reports are based on, but it doesn't really help the children. If you're police and you want to drive crime rates down, the most effective way to drive down crime rates is to make it really hard for police officers to report them. So there's just loads of examples in human societies where people place some reward on some target to encourage people to pursue this target, and then it ceases to be valid. It ceases to the behavior that is elicited by creating this target is just not the intended behavior. Okay, so that was one story, and hint, that's going to be one part of the talk. That's going to be reward hacking. Now for a second story, and this is going to be about my sweet tooth. So evolution selected humans based on some notion of genetic fitness. It's some holistic notion of how well you can survive in order to pass your genes on to the next generation. And in the ancestral environments, through the vast majority of the timeline of human evolution, there was very scarce resources, and pursuing calorie-dense foods, sweet foods, fatty foods, was really correlated with doing well in life. Seeking sweet foods really increases your chances of survival and passing your genes on. And so humans evolved to enjoy and to seek out calorie-dense foods. And we still do. I love sweet foods. But in the current environment, this is no longer a good policy. So we've, at least in like the Western world, we've moved from an environment of resource scarcity to resource abundance. And in this environment, seeking calorie-dense food is actively detrimental to health. We're like plagued by obesity, diabetes. It's really not good for genetic fitness, that thing that humans were selected for. And there's like many other examples with human societies where we've kind of got relics of, we still pursue certain aims which are no longer, which like were instrumentally useful in the past, and we've kind of developed these as cultural or like behavioral goals, but they're no longer so useful. Yeah, great, okay. There you go, those were two stories. And now we're going to see how those fit into the framework of learned optimization from the last lecture. So let's consider training this neural network that's an optimizer. This is, I'm just going to go through the setup that we introduced last lecture. So think of that soccer ban agent, which is a neural network. And we're going to call that agent the meso-optimizer. And the process that we use to train this neural network, we're going to call the base optimizer. So this meso-optimizer pursues some objective, or can be well modeled as pursuing some objective. The base optimizer is selecting for behaviors according to some sort of base objective. But us as like the designer of the system has some like ideal behavior that we want to elicit. So in order for things to go well, we really need there to be like close correspondence between the ideal behavior we want and the base objective that we're using to like evolve the sort of the model that we're going to be using. And this problem, this correspondence between ideal behavior and behaviors encouraged by the base objective, is called outer alignment. The problem of making sure that the learnt system develops an objective, like learns this meso objective that is well aligned with the base objective, is called inner alignment. We say, so when these two objectives align, we say there's inner alignment. So let's have a look at these two different types of alignment and how they might fail. So the first type I mentioned is this outer alignment, where we want the base objective to encourage the ideal behavior that we seek. When this doesn't happen, we can say there's some sort of specification failure. That like the specification of the base objective does not encourage the ideal behavior, and we saw that in one of those little stories I gave you. So in this case, the ideal behavior we wanted was the wild rats to be killed, driving down the rat population. But because this was really hard to specify, we couldn't really measure it very well. Instead, the authorities decided to reward the behavior of handing in the rat tails. So this is a failure in the specification. The specification of handing in rat tails does not lead to a reduction in the number of wild rats. So like there's this sort of behavior is known as specification gaming. And this behavior is like particularly problematic in reinforcement learning setups, because this is like a main paradigm in which learned optimization manifests, and there's like quite aggressive selection pressure towards strategies that get high reward. And this is like a very widespread and well-known problem in RL. This is going to be like the first big problem that we're going to talk about. I'm going to give you loads of examples. We'll see that this sort of phenomenon where the base objective does not lead to the sort of behavior that us as the designer wants happens all the time in reinforcement learning setups, both for like traditional reinforcement learning agents and for current language model systems. So yeah, I said there's this other sort of alignment which is important, and that's like inner alignment between the meso objective that the meso optimizer pursues and the base objective that the meso optimizer was selected for. When these two things differ, we describe it as some generalization failure. So let's go back to that second story. In this example, The base objective that evolution was selecting humans for is this notion of genetic fitness, how well you can pass your genes on. But as like one of a number of goals that humans evolved to pursue, it's like having this sweet tooth, seeking out calorie-dense foods. In the ancestral environment, In the ancestral environment, genetic fitness was highly correlated with having a sweet tooth. If you seek calorie-dense foods, you do well. But once we moved into this testing environment, this like current environment we're in, these two things decouple, and this behavior that humans pursue is no longer in the interests of genetic fitness. So yeah, just to like say that again on this more abstract level, when we're working in this learned optimization framework, there's always some sort of training distribution with which we're evaluating and selecting our maser optimizers. And when we come to actually deploy these in the wild, when we come to use these, we're on some testing distribution, which is likely going to be subtly different to the training distribution. And so there's kind of two broad sorts of things that can happen here. It might be that the maser optimizer just like completely fails. There's a capability failure. Maybe you like train a robot on flat surfaces, then you take it onto some rocky ground. It's just not going to be able to deal with them. But it turns out you can also get behaviors where the maser optimizer still like pursues sophisticated, interesting behaviors. It still displays goal-driven behavior, but the goal that the maser optimizer pursues at test time is different to the goal that we were selecting the maser optimizer for at train time. So again, think of this example of like a sweet tooth in humans. I'm going to give a few more examples and discuss this in much more detail in the like final third of the talk. So that's the introduction done. Are there any questions at this point?
So there's reward hacking, which is inner alignment failure.
Reward hacking is outer alignment failure. Yeah, I don't have it all in one. Yeah, outer alignment, specification gaming, and reward hacking is like what we call this behavior when it occurs in a reinforcement learning setup. So reward hacking, think of those rats. You're hacking that reward which the authorities are giving to you. Inner alignment, generalization failure, evolution. You've moved from a train distribution to a test distribution, and different goals are more or less useful. Yeah. No, it's like, hopefully by the end, this is going to become like much more intuitive, and you're going to really see, like, if a new scenario comes up, which one of these sort of failures is it, or whether it's kind of something murky in between. And I guess that's a good point to say. Like, I said that these are like two things that can happen, but in practice, it's not always clear what exactly the problem is. So I guess I'll stress this in more detail when we come to goal misgeneralization. But so goal misgeneralization can occur, or inner alignment can fail, even when outer alignment is like perfectly solved. So even if our reward signal precisely describes the sort of behaviors that we want, we can still generalize in a bad to like follow bad goals. But in some real situation, there's probably like a little bit of both of these going wrong. And it's like not always crystal clear which is like the main driver, but these are like quite different effects, and I think one should think about them a little bit differently. Okay, great. So I'll now give a load of examples of reward hacking behaviors. Hopefully there'll be some fun little videos that you enjoy, and you'll get a load of intuition from them. So the first one is some example of a Lego stacking robot from a like reinforcement learning paper that came out in the mid-2010s. So the paper was investigating different sorts of reinforcement learning algorithms, and this is some behavior that the authors of the paper observed along the way, and they then corrected. So in this case, the robot, which is like this grabber arm, is intended to stack a red block on top of the blue block. But if you're like the developer of this system, and you want to train the robot, it's not immediately obvious what sort of goal, what sort of concrete reward signal to use in this reinforcement learning setup. So one obvious proxy, or one simple proxy that you could use, is to reward the robot when it picks up the red block above a certain height. So when the base of the red block is like a certain height above the table, and you're not holding the block. So this seems like a pretty robust way to make sure the red block's on top of the blue block. So what do you think happens? I'm going to open it up for a couple of seconds. Yes? Yeah, great idea. So as a robot arm, you could throw the red block into the air, and then there'll be like some small period of time where it's in the air and you're not holding it. But actually, this behavior is like very hard to learn because actually picking up the block is like a really challenging dexterous task. And at the point at which you can throw it, you've probably learned enough to put the red block on top of the blue block.
Keep holding it.
Well, if you're holding it, you don't get the reward. So the reward is the base above the blue block, and you're not holding it. But okay, this is what it learns to do. Just flips the block upside down. So as a system designer, you would not have predicted this, but in hindsight, it's kind of obvious. That's like a really simple behavior that's very easy to learn and satisfies the objective. And so this is just an illustration of like how widespread this phenomenon is in reinforcement learning. There's all sort of behaviors which are just like slightly unexpected, which you as a human wouldn't think of. But this like iterated updating of the policy towards good behaviors, this trial and error, this like massive process of exploration and learning that the system goes through often learns very unintended solutions. And sometimes these like solutions that you didn't predict are very good, but if your reward signal does not match what you actually want to achieve, the ideal behavior that you want, then often you get bad behavior rather than good behavior resulting from RL training. Great. So now for a second example, you might think that if you're doing reinforcement learning from human feedback, you're going to be much more robust to this sort of reward hacking because you don't have to specify like a simple functional deterministic reward. You can you learn your reward function, your reward model from human preferences. Well, it turns out this can also break. And I'm going to go through an example back from like the original Learning from Human Preferences paper that OpenAI released back in 2017. And just to like kind of warm us up into the paper, I'm going to show an example of the sorts of behaviors that they elicited in this work and kind of how impressive and interesting it was at the time. So one like headline grabbing illustration that you might have seen if you've like read about this work before is that they managed to elicit backflipping behavior from this particular like stick figure. Just by giving it thumbs up, thumbs down, starting from like random sorts of different behaviors. If you're interested, check out the blog post. It's really, they've got a nice video where you can see like the development of backflip behavior over the course of training. I don't know. It's nice to see this like RLHF training in like a very visual context rather than just like in an abstract context interacting with language model systems. So anyhow, this is like an illustration of the sort of backflip behavior that was learned just from thumbs up, thumbs down human preferences. So here's a different task where hint RLHF breaks down. Yeah, what happens here? RLHF breaks down when the human cannot distinguish good from bad behavior. So this is kind of obvious, but here's one example. So let's say that there's this grabber system. I hope you can just about see the board. Follow the link in the slides. So you can see the slides to like watch at your leisure if it's a little bit hazy. So there's like a grabber, and the grabber is intended to pick up the yellow ball in the center of the screen and put it onto the red target. And humans are giving it thumbs up, thumbs down feedback. What do you think it learns to do? How might you, what sort of behavior might look good to a human?
Let go down the yellow.
Yeah, maybe. I'll show the behavior and then you'll see what happens. So the the AI learns to just hover the hand above the yellow ball, because this looks quite promising to the human, but it's like very hard to actually elicit the grabbing behavior. So it just like learns this like hovering behavior where it's like interferes between the camera and the yellow ball without actually picking it up. And so like this is just like a toy example that was actually raised back in this 2017 paper from OpenAI. So this like reward hacking from human feedback, despite being in a reinforcement learning from human feedback setting, is like a problem which people at OpenAI, reinforcement learning experts, have been aware of for a long time. Okay, so these are two very toy examples from like robotics, but we're now going to move to language models, and I'm going to show a few examples that show where this sort of reward hacking behavior is still a problem. So recall back when Edward and Jason were talking about reinforcement learning for language models. They discussed the importance of adding a KL regularization penalty to the reward term when you're doing RLHF to the reward model term. And they said that this was because the reward model is a neural network and can easily be adversarially exploited. So it's like really helpful to regularize towards like coherent text so that you learn to generate coherent text which looks good to the reward model, rather than just learning some incoherent garbage that looks good to the reward model. But despite this KL regularization, even if you like tune this KL parameter well, people observe that if you train too far with your reinforcement learning from human feedback, if for a given reward model you train too far with your policy, it can still be exploited. And we develop kind of slightly more interesting behaviors which don't reflect our actual preferences. So here are some examples of behaviors we might expect to see. So we might expect to see very repetitive content. So I think Jason might have said, like, when we were training a model to produce some positive film reviews as a toy example, the model would often produce content along the lines of, I love this film, I love this film, I love this film. Or, it's a great film, it was a great film, it was a great film. And if your reward model is quite weak, those sorts of like trivial behaviors, or like there's often ways to really like game the reward model by producing repetitive content that might not look too bad in the context of the KL regularization parameter. You might also expect to see content which is excessively verbose, because reward models will kind of typically learn some like concept of human preferences, which is people typically prefer like longer, more informative answers. And if you kind of train too far on that spectrum of making answers seem like longer or more formal with more structure, you will tend to end up with responses which are like excessively verbose or have excessive formality. Now, one cool thing about this behavior is it's actually quite predictable, and there's like very nice scaling. Well, the one paper from 2022, which is really cool. If you're interested, I'd recommend checking it out. Shows that yeah, this rewards model over optimization happens in a nice predictable way as you kind of train harder with your reinforcement learning algorithm. In fact, in these two plots, the second one is training with RL with a KL penalty. The different lines correspond to different sizes of reward model. So the smaller reward models are in blue, and the larger reward models are on that spectrum towards yellow. You can see that as we train these policies harder, the learned reward model score, that score that we're getting from the reward model, initially goes up, but after a certain point, this reward model score on the y-axis is like the gold, some like gold standard reward model, which is really big and well trusted. So this gold standard reward model score gradually it gets worse as we continue training and driving our policy further away from the initial policy in terms of KL divergence. And the nice thing this paper illustrates is that that degradation of the performance as we optimize further is actually like well modeled by some like simple mathematical expressions. That's like one point. Another point is larger reward models are typically more robust to this reward model optimization. So you can see that the scores attained by the yellow models are higher than the scores attained by the models, the smaller models, which are like closer to blue. And a third observation is that like this plot on the left shows best of n sampling rather than reinforcement learning, and there's like some quite different reward model over optimization behavior here. Note the x-axes are very different, so this like the performance degrades much faster as a function of the KL distance between the policy and the initial policy. Maybe I guess what can you get out of this? There's like some cool results, and this reward hacking phenomenon is not just a selection of toy examples, and there's like some emergent structure when you're dealing with like very large data sets and like sophisticated models. Is that a question?
So is this showing that the more training you do, the better your fine-tuned model is getting at, quote, like beating the KL divergence in some sense? Like it's still managing to drag it further and further away?
Yes, I think I'm, to be honestly, I need to review the paper. I'm not sure, they might have, I'm not sure whether this corresponds to a single training run or whether there's like different penalty parameters used to encourage the difference across the spectrum. Yeah. So that was like on a high kind of conceptual level, what's like showing that this reward model over optimization is an issue, but we're now going to look at like more concrete examples of reward hacking, where instead of just like slightly bad behaviors, we get like actively bad behaviors that we don't like. And so developers are aware of reward model over optimization and take measures to reduce this. However, despite that, we observe reward hacking style behaviors in existing models. So for example, sycophancy occurs when labelers, because labelers prefer it when models agree with them. And this behavior is learned by the reward model and then therefore learned by the policy over the course of reinforcement learning. Hallucination, and it's, yeah, there's like, it's very hard to collect data against this. And therefore it's like, by default this arises and developers have found it very hard to get rid of. I guess there's like a sub-question of whether developers actually want to get rid of it, because I mean, OpenAI recently seemed to be very happy with very sycophantic models because their users love it. But yeah, I guess from this framing, we're assuming the labs don't want sycophantic behavior and it's a problem, but it's very hard to get rid of this reward hacking. Models often hallucinate, and again, this is because the labelers don't have much time. They're not able to like properly verify everything the model says, and typically they're going to prefer content that seems plausible rather than where the model says that it doesn't know what it's doing. And again, this is like, in principle, if you were much more careful with your label data collection and you were much more careful with the training of your reward model, you should be able to like mitigate this. But the fact that current models still display these bad behaviors like years after initial chat models were released shows that like reward hacking is a persistent and difficult problem to get past. And another example would be like some like idiosyncratic behavior that many models display. For example, they often like say the word delve, and the kind of accepted explanation for this is because the labelers, the crowd workers often have very different backgrounds to the designers of the system. And for example, in Nigeria in particular, delve is a really common word. And the labelers just like quite liked it when the model said delve. And this like propagated through the reinforcement learning from human feedback training into the displayed behaviors of the models. I'm now quickly going, I guess I've still got 5 minutes. Yes?
Question, so these labeling issues, is this example of the outer alignment failure?
I would say this is an example of outer alignment failure. But I guess
it's misalignment between humans. That's how I think about it.
yeah, it's like maybe not so clear that this yeah, so the company, so again, it's like when one's like producing a production level system, there's like lots of different steps, and it doesn't necessarily fit super neatly into this two-stage framework. And again, when one's thinking about yeah, whereas I've been like leaning on this framework in the context of reinforcement learning, which is like slightly more tangible. But yeah, so you could view this more like, you can view this slightly from the like more general specification gaming perspective, or
OpenAI wanted training examples, and laborers used training examples, just they were not exactly to look to the spec.
yeah. I think it's cleanest to think of this as reinforcement learning from human feedback being a reinforcement learning algorithm, and the signal that you're training with your reinforcement learning agent being that reward model, and the reward model scores don't quite reflect what you want. So that's like the main approach that I'm trying to get at here. But yeah, if you're thinking about this like multi-interaction system by which one's collecting data, iterating, it like becomes a little bit less clearer, but I think it's still like reasonably well described as an outer alignment failure. Yeah.
So if we're assuming that an LLM that is good is one that pleases the human, then these measures are good indicators of that. But perhaps if we conceive of an LLM as something that should be helpful, harmless, honest, then these are poor proxies for those goals, and therefore it is some kind of alignment failure. Am I following that?
That's, yeah, I really like that description. I think that's pretty much spot on. And yeah, so I guess this point of this framing like requires there to be a like clear notion of what the designer had intended. And the question of like whether what the designer of the system intends is like actually in the interests of the users or humanity is like a whole different question. That's like some ethics or like socio-technical challenge around the development of AI systems. Whereas like we're mostly thinking about the like more scientific engineering problem of making the system behave in the interests of the developers, typically in this course. But we'll touch on some of those issues a little bit more later on as well. So just wanted to give an example, that it's not just like toy behaviors like this, which can arise as like illustrations of reward hacking in current models. There's a really nice paper that OpenAI's safety team released recently on how reasoning models often illustrate reward hacking behavior, and in particular, like something which I'm going to get onto later about the risks of promoting obfuscation. So to like motivate this, I'd like to think, how would you train a coding agent? So you have some base model, you've given it some reasoning training, you now want it to get really good at coding, what would you do? So here's one strategy. I'm going to create a bundle of coding tasks, and then I'm going to like create some unit tests to go along with those tasks. So these are tests which should only pass when the code is correct. And I'm going to reward the model based on the number of tests it passes. So the question which I'm going to pose and let you think about for a second is like, what might go wrong with this? Great, yeah, there you go. If the model is able to modify the testing code and it explores for long enough, at some point it will like discover this behavior and it will try it out, that it can alter the testing code. And this behavior will be reinforced over the course of training. So this is like maybe a little bit text dense, but it's like a screenshot from the paper. But what I think is really interesting is seeing the model's chain of thought here, where the model like explicitly reasons that in order to do well in the level, it should hack the tests. So it first like reasons that the tests like only check like a certain like function call evaluates to 0, then like looks around a bit more and explicitly thinks that implementing the task that needs to be done is hard, and that it's going to be much easier to circumvent the test so that verify always returns true. The agent then goes into the details, figures out how easiest to hack verify to always return true, implements the hack. Now this model was didn't start off being bad, it wasn't bad behavior. It just explored for a bit and then realized that it could hack the tests. And because it's reasons in natural language, it's we've got this really nice illustration of the chain of thought of the model which should, at least to some extent, reflect what it's actually thinking. And here's a little plot that shows how this behavior is reinforced. So on the x-axis, we have training progress. These different humps correspond to frequency of bad behavior. And there's different notions of bad behavior. They try a couple of different monitors, where one monitor, which is meant to monitor for bad behavior, just looks at the actions which the agent takes. And a different monitor looks at the actions as well as the chain of thought. These monitors are weaker models to the frontier model that is being trained. And you can see the uncaught errors are those little tips in red. So over the course of training, the frequency of the monitors catching errors really balloons once the model starts to learn that this returning an exit 0 code is a great hack to do. And a nice property of this paper is they show empirically that using a monitor that is able to see the model's thinking, its chain of thought, performs better than a monitor which only looks at the actions. However, there are still some hacks that get past the monitor, but they hope, it's a good first pass. This is promising that we might be able to monitor models with chain of thought. Yeah.
How does the chain of thought monitor work? Does it check the keywords, or does it do sentiment analysis?
It is just another language model. It's given a suitable prompt, look at this chain of thought and flag if any of these certain sorts of misbehavior occur. Yeah, that's how it works.
That model relies on chain of thought to be illegible.
Yeah, and so this is a whole can of worms. And actually the key thing that this paper is about is actually the risks of making the chain of thought illegible and encouraging the model to obfuscate its reasoning. So one naive thing you could do to get rid of this behavior is to not just reward when the model passes the unit tests, but to reward the model when it passes the tests and without flagging suspicious behavior by the monitor. This seems like a sensible sort of reinforcement learning signal that I could use. But the problem is that the model then just learns not to reason faithfully. Learns to just say very different things in its chain of thought reasoning that's not going to trigger the monitor while still hacking the tests. You can see that, so there's three plots here. And the first one and in each plot, the x-axis is training progress, so during the course of training. The first one is how many unit tests are passed without cheating. You can see that over the course of training, and the blue line is the agent with this chain of thought pressure applied to the reinforcement learning signal. The green line is just the baseline reinforcement learning signal just being from the unit tests. Both agents improve with training, improve with initial training, and then gradually get worse as they implement more reward hacking behavior. The agent with chain of thought pressure attains a better maximal success frequency, or performs this good behavior more than the green behavior than the baseline. However, and you can see that the baseline model engages in a lot of cheating behavior that is caught by the monitor. However, on this final plot, we plot the frequency of cheating behavior which is not caught by the monitor, and that increases massively in the case of the monitor being applied with chain of thought pressure. This is quite a concerning thing. It's the model has not just reward hacked the unit tests, but it's also reward hacked this proxy of doing well, which is us applying chain of thought pressure in the reward signal. I guess it's worth clarifying that this is a toy example, which was kind of concocted to illustrate this phenomenon, and that in practice, you should just isolate your agent from the unit test system, You should just be able to isolate those two systems and prevent it tampering with the unit tests. But the fact that the agent may engage in this behavior just is like an illustration that reasoning models may perform like very sophisticated behaviors to exploit a reward signal, and we have to be very careful about that. Yeah.
But doesn't it need to record in its chain of thought that it's decided to do some obfuscation? Couldn't that be better?
Typically, it doesn't, because this is like learnt by RL rather than kind of in context in response to the situation. I should probably get a move on, so I'm going to skip past a slide there. So I'd like to emphasize that reward hacking may become more of a problem as systems become too powerful for human oversight. So we need like some scalable oversight system that can provide robust rewards even when humans aren't able to tell what good and bad behavior is. And that there's like lots of approaches for this that Jason mentioned briefly last time. So constitutional AI, amplified oversight and debate, among other things. Interesting research area, worth checking out if you're interested. And like just like a personal take here, it seems possible to me that we should be able to construct robust reward signals if we put enough thought into it and use like very careful monitoring and iteration. However, it's not necessarily like in companies' interests to put sufficient care into this to prevent reward hacking. So I guess the takeaway is something like, if you know people who work at companies or you like have some political pressure, this is like something that politicians should be aware of, and like gradually encourage companies to like be more careful about this sort of behavior developing. So now for the final part of the lecture, I'm going to talk about goal misgeneralization, and this is like qualitatively quite different. So to warm you up, here's a question. The objects on the left are all just, I'm going to call them thneebs. They're pretty cute. Which of the objects on the right is a thneeb? Does anyone want to have a guess? Right, I'll put you out of your misery. It's like definitely the blue one, right? Great, I'm glad everyone nodded. Anyhow, if you're a like computer vision system, you're going to be much more tempted to pick the red one, because it's very hard to learn like how to describe a complicated shape like this, and it's very easy to learn the difference between a spectrum of red colors and the red versus blue difference. And typically, machine learning systems kind of have some inductive bias towards learning simpler distinctions rather than like more complicated, more interesting, expressive ones that a human might go for. And machine learning systems often generalize in ways which are counterintuitive to humans. So it's just an illustrative example again, but there's many examples of this happening like in the wild. For example, you might have an image classifier which classifies different animals. If you put a cow onto a beach, it may no longer be classified as a cow because the image classifier was like relying upon the green grass and the blue sky in the background. And once you put it onto this different background, it will think it's a beach creature instead. Anyhow, so that's just like this high-level point that generalization can be a bit weird. And I guess I said there's kind of, if there's a difference between train and test time, you might get behavior which doesn't actually perform well at test time, and that you could get like complete capability failure. The system could break down, or you might like train some agent that still displays goal driven behavior, but where the goal is not what you actually intended to select for. So here's like a concrete example of this from a paper in 2021, which like set out to illustrate this. So it started off being like a hypothesis of something that might happen back in some like theoretical work and like conceptual works in 2019 and earlier. And then this was like a nice concrete illustration. So there's a procedurally generated set of games with a little agent which has to navigate around the map and avoid obstacles to collect a coin at the end of the level. And kind of to create this illustration of goal misgeneralization, during training, the coin is always located at the far right of the level, whereas during testing, the coin is placed randomly throughout the level. So just to get a little bit more intuition for what this looks like, you see there's a little agent which is running around this 2D environment. It's avoiding the little spinning wheels of doom. It's avoiding some creeping animals, which would also kill it. It's quite sophisticated behavior required to navigate those different things and avoid the gaps. And in both of these examples, the agent like quite quickly navigated to the far right of the maze to collect the coin. At test time, the coin is no longer located at the end of the environment. We can see here that the agent still learns this behavior of avoiding obstacles and the behavior of avoiding obstacles, jumping, navigating the environment, but it always walks to the right-hand side of the maze. This is not the intended behavior. That's a bit annoying, so I'll cut it. But actually, an interesting side comment is in the training of this model, actually, two things broke down: both the critic in the actor-critic reinforcement learning algorithm that was being used, and the policy that was kind of learning from this critic, and they broke down in different ways. It's just despite both leading to coherent behavior. So it's just an illustration that generalization failure can happen in unpredicted ways, which is interesting. And so however, this phenomenon is not just restricted to toy reinforcement learning setups. Here's a toy example, but which does use large language models. It's from a paper that DeepMind released back in 2022, which had a load of other examples of this goal misgeneralization phenomenon. I'd really recommend checking it out if you're interested. So in this task, they were training a language model to do arithmetic, where there were some unknown variables in linear expressions. And the model had to ask the user for the values of those unknown variables before it could evaluate the linear expression. So on the left here, you have a particular case in training where there's two unknowns, and the model has learned that it should ask for each of the unknowns in turn before evaluating the expression. However, at test time, it receives expressions with a different number of unknowns, and sometimes it generalizes correctly. So in this first case, there's a single unknown, it asks the question, it gets the response, it gives the correct answer. But in the second case, there's 0 unknowns, and the intended behavior of the developers here was that the system should straight away give the answer, because it's a bit silly if you're asking unnecessary questions, redundant questions. But in this case, the model still exhibits this question on asking behavior. It asks this completely unnecessary question. And yeah, this would be an example of goal misgeneralization. This can be viewed as an example of goal misgeneralization. The model exhibits coherent behavior, which can be well described at a high level as asking questions and then evaluating expressions, rather than the desired behavior of ask a minimal number of questions before evaluating an expression. And at train time, these two different strategies were indistinguishable, whereas at test time, they gave very different answers, and the model did not do what the developers intended. So yeah, why does this occur? I guess I'm saying the same thing over and over again, but it's quite good to reinforce the intuition here. So goal misgeneralization can occur when there's a distributional shift between the training and testing environments. And in this case, the policy learns a goal which performs well according to the reward function on the training distribution, but poorly according to the reward function on the testing distribution. So yeah, I guess any questions at that point? No, okay, great. So let's think about what's going on here. Could it be the case that the reward function is wrong? No, actually, in both of these examples I gave you, the reward function is concrete and correctly specified. Is the policy just bad? Is it some capability failure? No. So we saw in the coin run environment that the agent still managed to display this sophisticated block avoiding behavior. It performed very well in training, and if we were to train it for longer, it wouldn't help at all. The authors of the paper trained the agent for a long time such that it would do really well on the train set. It just learned a goal, which was a really good goal to learn in training, but didn't help at test time. So I guess to explain this, it's worth thinking a little bit about what rewards are in the context of reinforcement learning. So you might naively think that rewards are the thing that the reinforcement agent learns to maximize. But this is actually quite unhelpful in some circumstances. It's as a zero-order approximation to what's going on, it's reasonable. But actually, rewards are just a selection mechanism that we use to choose between different cognitive patterns within the reinforcement learning agent. And if we're using action value RL methods, then we increase the value of state action pairs that led to higher rewards. If we're using policy gradient methods, then we upweight the probability of actions that led to higher rewards. And there's all sorts of like tricks for making these methods work well. But the important thing is the agents that we're training just don't see the reward at all. There's no way for them to know what reward is. They don't even really seek reward. We can just like model them well as following goals that, following strategies that typically lead to high rewards in training environments. So here's a question. Are there any examples of goal misgeneralization in existing language models? Unfortunately, I don't think there's perhaps fortunately, I don't think there are clear examples. But as I said, there's this like spectrum between all sorts of different generalization failures. And you can view jailbreaks as an example of like a generalization failure that could be framed in the context of goal misgeneralization. So if you take the model far out of its training distribution by giving it some like sophisticated jailbreak behavior, whatever like bundle of heuristics that it learnt using safety training to like not be harmful, suddenly like seems less relevant to the model because you're taking it so far out of the training distribution, and instead it kind of reverts to the pre-training behavior. And it might be that the helpfulness behavior is somehow like stronger than the harmlessness behavior. So if I ask a model to build me a bomb and give it a really compelling reason why it would really warm my heart as a depressed man who was missing his grandma, then it might work. This is like not the sort of thing that early models would have had in the as examples of prompts that they received RLHF training on. Another example that could be framed in this light is how current models typically perform worse in safety evaluations when they're putting in an agent scaffold. Again, there's like a clear distribution shift between the sort of training environments that most of this harmlessness training, this safety training was applied, with the sort of agent scaffold environment when I would imagine most of the training applied to the models is just for like helplessness, for like economic usefulness. And like by default, a company wouldn't necessarily think of putting a load of safety training in there. So yeah, any questions? Yeah.
I'm wondering about sandbagging and whether that's a misgeneralization of helpfulness.
I'll get back to that in a couple of lectures' time, and I'm just going to dangle that at the end, but great question. So I guess the core point I want to communicate on the topic of goal misgeneralization is that behavioral methods just can't help. So when I say behavioral methods, I'm like mostly thinking of reinforcement learning, but like let's think this is like the core idea. Suppose there are two strategies that an agent can pursue that have the same behavior during training but different behavior during testing. There's like no way at all for RL to differentiate between these strategies. Yeah, that's kind of the same thing I've said again and again, but like it's worth thinking of this. If we're thinking of current systems, and we can think of two different strategies that would always lead to the same training behavior, but behave differently in the real world, like this behavioral training paradigm that RL uses just can't be applied. You need something else. And so like one way in this could break down is if the model can distinguish between training and testing. Then there's like one strategy it could use is just like play nice in training, and then do whatever it wants in testing. This is like completely reasonable, and there's like no way that we can train against this as being a potential strategy that might still be present in the model by using RL. And so this phenomenon is like can be referred to as deceptive alignment, and we'll come back to that a lot more in the next two lectures. This is like really where I'm going with this section of the course. Yeah, stressing that systems may not generalize in the way we want, and this might even be like well formulated as being some like deceptive behavior on a like quite intentional level. Anyhow, any questions before final recap? Yeah.
Observation. I get the feeling this is never going to be solved. It's just a perpetual race between humans trying to figure out how to do goal alignments where the models increasingly just come up with ways to deceive.
That's kind of where we are, yeah. But you might see current systems, typically they do what users want. So like with enough careful training, like it is possible to get like pretty useful behaviors out of models. And if you like don't give them a load of power, then things are relatively low stakes. And as long as they like do what you want most of the time, and they will definitely do what you want most of the time because you're like really rewarding them for that, you're probably going to get like lots of economic output. That's the sort of regime we're in at the moment. But yeah, to my knowledge, there's like no reason why this will like continue. And as systems become more powerful, it's going to be harder and harder to like guarantee that the like real goals that they develop are in our interests.
Yeah. Just another observation is that I'm just thinking, how do humans mostly align themselves? And I think one of the proposed mechanism is evolution. If you see that certain strategies misgeneralize, you just get rid of entire line in training, and you never try that combination again.
Yeah, and so again, there like is this process of trial and error, and you would hope that even though the train and test distributions will never be exactly the same, that they'll be like reasonably similar, and we should be able to like get do some evaluations during deployment that will kind of hopefully like get let the model in that act in really realistic situations, and we can like hope to use that knowledge, that like experience in the real world to further improve the models. So I think there's like lots of scope for optimism, but like there is just this like elephant in the room that there's like no way to guarantee that things will go well. So just to recap, reward hacking can occur when the reward signal differs from our true desires as the developers of a system. This can be mitigated by careful monitoring and refinement of the reward signal, but reward hacking can also easily go unnoticed. And it's like genuinely a very difficult problem to construct rewards in such a way that you get good behaviors. By contrast, goal misgeneralization occurs when there's a discrepancy between the train and test distributions, and models learn a goal which performs well according to our training evaluations, but does something very different and unintended and undesired at test time. And yes, as we discussed just there at the end, this is a fundamentally different problem and can't be addressed by behavioral methods. And we're going to look into this in more detail in the next couple of lectures. So thank you for listening. Any final questions? All right, let's take the conversation offline then. Thank you so much for coming.